I've been describing the type checking function, but in a different kind of notation than we usually use. This turnstile, colon, horizontal bar notation. I'm defining a type check function, but let's go back and do this all again in a more familiar notation. Let's write our type checking function in Plait. And as we do that, we'll make the usual sorts of simplifications. Let's have expressions that are just numbers, plus and times, single argument functions, but we're going to keep the part where in our lambdas we declare what the type of an argument is, because we need to put that environment in the environment as we type check the body. And then we have single argument application. In addition to defining expressions now, we also need to define what are valid types, because that's part of our grammar right here. And a type is going to be literally NUM, or literally BOOL, or it's going to be formed with a parenthesis, some type, an arrow formed as hyphen greater than, and then some other type, and then a closing parenthesis. So we have ways of writing expressions. In those expressions, sometimes we have to write a type, and so now we have a way of writing types, and this arrow has other references here, so we can build up types like num arrow num or num arrow bool. We can represent these things in the usual way, so here is our usual Plait definition of exp that has all of the usual variants. But in addition to this now we have a reference to type here, so we need to define Curly's types as a Plait data type. So we have a new data type type with a capital T, right? So this is a new type that we're defining. It represents Curly types, not Plait types. And we have three variants: a number type, a Boolean type, and in our concrete syntax, NUM is just the literal NUM, so our numt variant doesn't need any fields. Our arrow t variant, on the other hand, has an argument type and a result type. So of course arrow t has those two fields, both of which are of type, type. And then we need a type environment. That's going to be a list of type bindings, which as we said is like variable bindings for runtime for interp, but it maps a name to a type instead of a name to a value. So we'll use tbind as the constructor for a type binding. And now we can look at type check. It's going to take an expression, which is what we put before between the turnstile and colon, and a type environment, which we wrote to the left of the colon, but now we'll move it to the more familiar second position. And what type check has to do is give a type to every expression. If it can't give a type to an expression, it can raise an error. What it cannot do is call interp. That's the whole game, is to type check without interp. Because if we call interp, it might go into an infinite loop, and we want to make a decision without actually running a program. So type check now is just another function that takes an expression. We know how to do these type case things. We consider all the cases. If you get a nume expression, then we have already decided in this other notation that it should have type number. So that means what we write in the Plait implementation is numt. How about a plus C expression? It has left and right sub-expressions. In this notation, we showed type check being called recursively on E1 and E2. So that's what we're going to do here. We call type check recursively on L1 and R, or L and R. We get two types back from those, but what this rule says is they had to both be numbers. So we can do a type case on the type on the result of type check to make sure that the left expression has type number. If it's not, then we're going to report an error. And instead of just using a raw error function, I got a helper function here called type error that will just make a nice error for us. Type error takes the expression that had the wrong type, and it takes a string that describes what that type should have been, right? Why it didn't match up. And in this case, if type check doesn't say that it has type number, then we just complain about L, saying we expected a num type. We do the same thing for R. R also has to have a num type. And if R also has a num type, then the overall type of the plus expression is numt, right? That's this num right here. We're returning after we've made sure left and right both have type numt. Otherwise, we complain about R. Mult is the same, so let's look at identifiers. If we have identifiers, then we've got a symbol. We should be looking for that symbol in the type environment. So let's have a type lookup function that's just like lookup, except it returns a type, and that's exactly what we wanted to return. If we have a free variable, then type lookup will complain, and again, we'll complain about a free variable before we even try running the program. If we've got a lambda, what our interpreter did was always return a closure value right away. But now we're type checking, and our type checking rule was not to return a type right away, but to inspect the body's type. So we're going to type check this body expression, but to do that, we need an extended environment, right? We need this environment here is not just env that came in, it's env extended with symbol mapped to tau1. So our symbol here is n and the type is argtype, so that's type check in an extended environment where we have a type binding of n to argtype extending the type environment that came in. As long as we get a type for the body, tau2, then we want to put that together as an arrow type with the declared type tau1. So we've got argtype, which is tau1, type checks resort, which is tau2, so we put it together with an arrow t. And that is type checking a lambda expression. That leaves application. So if we've got an application of a function and an expression and an argument expression, what do we do when we have an expression? We type check it. And so we type check fun and arg, and we will get 2 types back. For the function type, it needs to be an arrow type. So we can do a type case on that result to make sure that we get an arrow t. And if we get an arrow t, we have an arg type and a result type. Now we need to make sure that this arg type matches the type check of the arg. That is, we need to make sure that this tau2, which is arg type here, matches the result of the recursive call on the argument expression, which is this tau2, which is that type check right there. So this result and arg type, we need to check whether they're the same. We can just use equal to check whether the types are the same type. If they do match up, then result type. All right, the second part of the arrow, this tau3 here, that's result type. That's what we wanted to return for the overall application. If they didn't match up, if they're not equal, then we need to complain. And we can say that arg, we expected it to have the type that was the arg type from the result of the function. Meanwhile, if the function expression didn't type check to an arrow type, then we complain about the function expression instead and say we just wanted some function type here.